Welcome to the podcast series The New Student Pharmacist, where we discuss chemistry and pharmacy, as well as leaders in pharmacy careers, community, and chemistry and pharmacy research. We encourage you to support the work we are doing and follow us on Spotify and Apple Podcasts by subscribing for free. Note, the views on the podcast represent those of my guest and I.
Have you ever wondered how we might apply the principles of Young's double-slit experiment to the design of quantum dots? Welcome to the captivating world of quantum mechanics, where the peculiar behavior of subatomic particles defies our classical understanding of the universe. The cornerstone of this intriguing world is the wave-particle duality, a concept that lies at the heart of Young's double-slit experiment. You see, this experiment elegantly demonstrates wave-particle duality, a fundamental principle that forms the basis of quantum mechanics. It's rooted in de Broglie's hypothesis, which suggests that all matter, especially entities as small as electrons, exhibits both wave-like and particle-like properties. Now imagine applying these principles to a quantum dot scaffold design. This intriguing concept is born out of Heisenberg's uncertainty principle, which states that we can't know both the position and momentum of a particle with absolute certainty at the same time. So we ask ourselves, can we emulate Young's double-slit experiment at the quantum dot scaffold level? Can we observe the same phenomena of constructive and destructive interference seen in Young's experiment? Could this venture provide us with a new understanding of multi-component radiation patterns? The key lies in the design and implementation of quantum dots. Imagine a quantum dot scaffold that mirrors the double-slit design used in Young's experiment, but on a much smaller scale. Such a design could potentially unveil unseen phenomena within the quantum realm. Furthermore, this integration could help us fine-tune quantum tunneling, a phenomenon that allows particles to pass through potential energy barriers that they shouldn't be able to cross classically. This is yet another fascinating aspect of quantum mechanics, and it too is rooted in Heisenberg's uncertainty principle. By integrating established concepts with novel experimental designs, we stand at the threshold of new applications that could revolutionize our understanding of the quantum world. And that's the magic and mystery of Young's double-slit experiment, a cornerstone in our understanding of the quantum world. Now, imagine if we could take these principles and apply them to the design of quantum dots. Quantum dots, nanoscopic semiconductor particles, are remarkable for their potential to manipulate the behavior of individual electrons. Their design, typically between 2 and 10 nanometers in diameter, allows for the control of electronic properties, such as charge and spin, making them a fascinating prospect for the application of the principles observed in Young's double-slit experiment. These quantum dots are not just small, they are minuscule, but don't let their size fool you. Their potential is enormous. Applying the wave-particle duality principle observed in Young's double-slit experiment to the design of quantum dots could open up new possibilities for observing unseen phenomena within the quantum realm. Envision a quantum dot scaffold designed to mimic the double-slit experiment. The quantum dots, featuring slits of the order of 0.1 angstroms or smaller, could potentially impart the same wave-particle duality behavior observed with light or electrons in the Young's experiment. But we're not just talking about the replication of the experiment at a smaller scale. We're talking about the potential for observing interference patterns at the quantum level, furthering our understanding of quantum mechanics. What's more, the integration of these experimental frameworks could yield insights into fine-tuning quantum tunneling, a phenomenon that allows particles to cross barriers they shouldn't classically be able to. This aspect of quantum mechanics, still ripe for exploration, could be illuminated further by observing the behavior of quantum dots designed to replicate the double-slit experiment. Through this integration of principles and designs, we stand on the threshold of uncovering new phenomena in the quantum domain. The potential for exploration is vast, and the implications of these endeavors could extend far beyond our current understanding of quantum behavior. The convergence of Young's double-slit experiment and quantum dot designs presents a promising frontier in quantum mechanics, one that could potentially revolutionize our understanding of the quantum world and its many mysteries. But what if we could go one step further? What if we could use this integration to explore multi-component radiation outputs? Just imagine for a moment a quantum dot scaffold designed and tuned to mimic the properties of Young's double-slit experiment. Now picture it in action, emitting a multi-component radiation output that's influenced by the unique characteristics of the quantum realm. This isn't just a fanciful idea, it's a potential reality, and it's one that could revolutionize our understanding of quantum behavior. By leveraging the principles of Young's double-slit experiment in the design of quantum dot scaffolds, we could observe a range of radiation outputs, each reflecting different components of the quantum realm. This could potentially reveal novel phenomena and interactions at the quantum level that were previously unseen or even unimaginable. But that's not all. This approach could also provide a powerful tool for fine-tuning or attenuating quantum tunneling. Quantum tunneling, a phenomenon that's deeply rooted in Heisenberg's uncertainty principles, is a fundamental aspect of quantum behavior. In conventional physics, we view the potential energy barrier as something that a particle must overcome. But in the quantum world, particles can tunnel through these barriers, thanks to the uncertainties in their position. By applying the principles of Young's double-slit experiment within quantum dot designs, we could potentially control or influence this tunneling process. This could lead to new insights into quantum behavior and open the door to innovative applications of quantum tunneling in a range of scientific and technological fields. To say that the potential applications are staggering would be an understatement. We're talking about breakthroughs that could redefine our understanding of the quantum world and pave the way for a new era of quantum technology. So, as we continue to delve into the mysteries of the quantum world, let's remember the power of integration and exploration. Let's continue to push the boundaries of what's possible, leveraging the principles of Young's double-slit experiment to reveal the potential of quantum dot designs and multi-component radiation outputs. The potential applications and advancements in our understanding of quantum behavior are truly staggering. The convergence of these principles and designs represents a promising frontier in quantum mechanics. We've examined the intriguing quantum world, delved into quantum dot designs, and unveiled the potential for multi-component radiation outputs. The integration of Young's double-slit experiment with quantum dot scaffolds opens a window of opportunity to observe and manipulate unseen phenomena within the quantum realm. The potential of fine-tuning quantum tunneling through such designs could further our understanding of quantum behavior, paving the way for innovative applications. This exploration isn't merely a scientific exercise. It's a leap towards the future, a step closer to unraveling the intricacies of the quantum world. The potential applications and advancements that could arise from this exploration are vast and exciting, from enhancing our understanding of quantum behavior to possibly developing new technologies. As we continue to explore and innovate, who knows what fascinating discoveries lie just beyond the quantum horizon.
Have you ever wondered how the tiniest particles can have the greatest impact? Welcome to the fascinating realm of quantum dots, where size isn't just about how big or small something is. It's a world where larger, uniform nanoparticles offer more space for electron waves, influencing their optical characteristics in ways that are really quite remarkable. But it's not just about size. These nanoscopic entities, these quantum dots, they exhibit behaviors that are nothing short of intriguing. When subatomic particles are confined within these nanoparticles, we see observable quantized effects. These effects dramatically shape their optical manifestations, turning them into a powerful tool for understanding the world around us. But what's truly exciting is that we're just scratching the surface here. There's so much more to explore, to understand, because in the world of quantum dots, size isn't just a measure of space. It's a gateway to a whole new perspective. Size, it seems, is more than just a measure of space when it comes to quantum dots. Let's dive into the deep end of quantum chemistry, shall we? When we talk about quantum dots, we're dealing with a fascinating interplay of principles that govern the quantum world. One such principle that's front and center is Heisenberg's uncertainty principle. Heisenberg's principle tells us that we can't know the position and momentum of a particle with perfect accuracy. The more precisely we try to measure one, the less precisely we can know the other. This principle is a cornerstone of quantum mechanics and has profound implications for our understanding of quantum dots. Now let's talk about size. In the quantum realm, size isn't just a measure of how big or small something is, it's a mathematical expression of position across a dimension or multiple dimensions. When we talk about the size of quantum dots, we're actually talking about the confinement of subatomic particles within a nanoscopic space. The smaller the quantum dot, the greater the confinement, and the more pronounced the quantum effects become. Quantum dots, these nanoscopic entities, are unique because their properties change with their size. Larger quantum dots offer more room for electron waves, which influences their optical characteristics. But it's not just about size. The way these particles are confined also influences their properties, leading to observable quantized effects. In essence, these foundational principles of quantum chemistry, like Heisenberg's uncertainty principle and the role of size and confinement, help us understand the intriguing world of quantum dots. They allow us to predict how quantum dots will behave and how their properties will change based on their size and the degree of particle confinement. These principles lay the foundation for understanding the intriguing world of quantum dots. But that's just the beginning. There's so much more to explore in the quantum world, and we're just scratching the surface. So buckle up, because we're about to venture deeper into the quantum realm. But what happens when we look beyond the size of these nanoparticles? What role does momentum play? Let's embark on an exploration of how the intrinsic and resultant momentum of quantum dots might impact their optical and temperature properties. The world of quantum dots is a world of fascinating possibilities. In this world, size isn't the only variable that has a significant impact. Momentum, too, can play a vital role, and the implications of this are far-reaching. Imagine, for a moment, a quantum dot. It's not just a particle, it's a dynamo. Its intrinsic momentum is the measure of its motion, the sum of its mass and velocity. Now consider the resultant momentum. This is the total momentum of a system of particles, considering both their individual momenta and the interactions between them. What happens when we introduce quantized light into this picture? The light, with its packets of energy called photons, interacts with the quantum dots, altering their momentum. This can lead to changes in their behavior, influencing their optical and temperature properties. This interaction could potentially give rise to a spectrum of radiation with tuned multi-components. With the right tuning, we could adjust the properties of the emitted light, leading to new possibilities in photonics and optoelectronics. Moreover, by understanding how quantum dots' momenta affect their absorption of quantized light, we could potentially improve our control over this process. This could have significant implications for applications such as solar cells, where efficient light absorption is crucial. Now, let's take this a step further. If we can understand and control the momentum of quantum dots, could we tailor this to meet specific needs? Could we design quantum dots with specific momenta to serve in diverse research and clinical settings? The possibilities are intriguing. The momentum of quantum dots, their intrinsic dance with light and energy, could open up new avenues for research and practical applications. This is more than just a new perspective on quantum dots. It's a perspective that could redefine how we understand and utilize these remarkable particles. The momentum of quantum dots could open up new avenues for research and practical applications. It's time to reframe our understanding of quantum dots and their potential applications. Historically, we've focused on the size and position of these nanoparticles, but there's an unexplored terrain here. Imagine the possibilities if we were to consider how quantum dots adjust their behavior in the context of quantized light when possessing an intrinsic or resultant momentum. Rather than being confined by the lens of size and position, let's venture into the dynamic world of momentum. This new perspective could offer a fresh approach to understanding the optical and temperature properties of quantum dots, potentially leading to tuned multi-component radiation. By focusing on the intrinsic and resultant momenta, we might even be able to manipulate the quantized light absorption of these particles, tailoring them to meet diverse research and clinical needs. As we push the boundaries of our understanding, who knows what new discoveries await in the realm of quantum dots? So what have we learned about quantum dots today? we've delved into the realm of quantum dots, exploring their size-dependent optical properties. We've discovered that larger nanoparticles offer more room for electron waves, impacting their optical characteristics, while the confinement of subatomic particles within nanoparticles leads to observable quantized effects. We've also pondered the foundational principles of quantum chemistry, with a special focus on Heisenberg's uncertainty principle and its implications on the momentum and position of entities at the quantum scale. We've dared to think beyond size and position, contemplating the role of intrinsic and resultant momentum and the potential effects on optical and temperature properties. We've asked probing questions, considering the possibilities of a radiation spectrum with tuned multi-components, and pondered how an understanding of quantized light absorption could be tailored to meet diverse research and clinical needs. The world of quantum dots is complex and fascinating, and we've only just begun to scratch the surface.
Thanks for listening to the podcast series The New Student Pharmacist, where we discuss chemistry and pharmacy, as well as leaders in pharmacy careers, community, and chemistry and pharmacy research. We encourage you to support the work we are doing and follow us on Spotify and Apple Podcasts by subscribing for free. We are so glad that you were able to tune in today. Note, the views on the podcast represent those of my guest, and I take care and all the best.
You are very important, especially to us here at the New Chemist podcasting group. You listening in is significant.
Vous êtes très important, surtout pour nous ici au New Chemist Podcasting Group. Votre écoute est significative.
Usted es muy importante, especialmente para nosotros aquí en The New Chemist Podcasting Group. Usted escuchando, es significativo.
Você é muito importante. Especialmente para nós do The New Chemist Podcasting Group. Você ouvindo, é significativo.
Είστε πολύ σημαντικοί, ειδικά για εμάς εδώ στο The New Chemist Podcasting Group. Το να ακούς είναι σημαντικό.
Sie sind sehr wichtig, besonders für uns hier bei The New Chemist Podcasting Group. Es ist wichtig, dass du zuhörst.
Je bent erg belangrijk, vooral voor ons hier bij The New Chemist Podcasting Group. Dat je meeluistert, is veelbetekenend.
You are very important, especially to us here at the New Chemist Podcasting Group. You listening in is significant.